Okay, so this video is about impulse, and when we talk about impulse, we're often linking it in terms of the change of momentum, and we can start talking about the force. So we start looking at a collision, and over a collision, we know that the momentum is going to change over a certain amount of time, and the amount of force is proportional to that change in momentum. So we calculate it using this way. So force is equal to the change in the momentum, okay, over the time. Now, again, in this case, if I plotted like a force against time graph, let's imagine, for example, we had a tennis ball, okay, falling onto a racket and then bouncing back off. Okay, as soon as it starts to impact, we're going to have a low amount of force moving up to our maximum amount of force. And then as it begins to rebound off the racket, it's going to, again, decrease that force in there. Okay, so again, we can start talking about that in terms of the size of the force, or the total size of the force, the impact of the maximum force equal to the change in momentum over the time. Now, what we then talk about in terms of the impulse, we define the impulse as essentially being the change in the momentum. So we actually just rearrange the equation and we say that force times time is equal to the change in the momentum. Now, again, often with this, we can talk about kind of the units that's given. If we're just talking about change in momentum, we still use kilograms, meters per second, but usually when talking about the impulse, we actually are using force times time, so our Newton seconds. Okay, so be really careful with that. Impulse usually is Newton seconds, unless you're having to do change in momentum and calculate it from the momentum side, then that would be there. The other thing then, looking at this force time graph, okay, so force times time is the impulse. The area underneath the graph, okay, is equal to the impulse. Okay, so force times time, but also therefore it's also equal to the change in the momentum that has taken place. So a few other things that they like about this often with these questions are in terms of like maybe a multiple choice question, what's the unit? They like maybe the graphing questions about calculating the area under the graph. Okay, they could get you to work out that's change in momentum. They might then ask you, maybe giving you some speeds on some values there, you might have to calculate the mass or vice versa. It might just be simply what is the area under the graph. Or they might actually give you some sort of written questions. So again, we're looking at our written questions with this and looking at the equation of that force as change in momentum over time. They often kind of bring in a question maybe linking to safety or some sort of impact or injury. So one of the ones that was previously on an exam was about landing on snow compared to landing on ice. Okay, you could have it with an airbag in a car. You could use it for like bubble wrapping. So why would you package fragile items within a bubble wrap? And you're often having to link back to the safety. So what you always want to talk about really is the size of the force that's taking place. So I'm going to use the snow and ice one as an example to kind of how we would structure this question out, or the answer to this. Why would you prefer to land on the snow compared to the ice? Well, if we're looking at the impact time, okay, we can see with the snow, it's lighter, okay, so it's going to compress more, so increase the time of the impact. So we'd say something like snow has a longer impact time, okay, or delta T increases, okay. Again, you'd have to write this in words rather than using the little symbols here. Okay, I like to use bullet points to structure my answers out. Now, if I'm increasing the time, the change in the momentum for snow or for ice is going to be exactly the same. Okay, so the change in momentum for both is going to be the same. Well, if you think about it, they're both falling with you, and their change in momentum, they're both going to go to zero. So that change in momentum isn't going to change. Okay, so the change in momentum for both is going to be the same. It doesn't change. So at this point, we start going back to the equation. Well, if this doesn't change and this is increasing, then the size of the force is actually decreasing. So I'd say, I'd kind of bring that in as my third point. So the force is decreasing, but I need to kind of back, oops, sorry, I realised that's not on the screen. I want to back that up. So I'm going to say since F is equal to the change in momentum over the change in time. If delta T increases, force must decrease. Something along those lines there. But again, you can structure this out in bullet points to explain. Again, if this was bubble wrap, again, the bubble wrap is going to be exactly the same. It's going to have a greater amount of time during something falling. Again, same with an airbag. The airbag increases the time of the impact or time of the collision. Okay, so impact or collision. We talk about it compressing, that's increasing the time. But essentially, the big point with this is that the change in momentum is going to be the same, and usually students forget to mention this part here.